And we're back, everybody, and we're rolling. All right, so this is the second day of section 1-1, finishing up the notes today. Yeah, tomorrow should be just a work day. If you have any questions, if you want to get a jump on your homework tonight, we might have a little bit of time in class. I don't know. I got long-winded yesterday, so maybe I'll get long-winded again today. I can
Just get an email about my class.
That's it. I see. It's like kind of like a visual thing. I can maybe see that for you.
Thanks.
Do you want to sit up or do you want to sit down? It doesn't
It
matter.
doesn't matter.
You can-
Fine, yeah.
There's plenty of seats to choose from.
Yeah.
So again, I hopefully get you some time in class today to work on it. But if you get a jump on the homework tonight, that's preferred, so that you can come in tomorrow and then I can answer any questions about anything that you have on the assignment. Or if you want to get can work on it tomorrow and midway through the period you want to ask some questions. Again, tomorrow is your time to get to work, and then again the assignment for 1-1 will be due on Monday. All right, so what were we talking about in section 1-1? The title of it is 4 ways to represent functions, or in my mind, I think it's just like kind of like a lot of review about functions. What does it mean to be a function? How many, or what are the things that we can define about functions? Remember, functions are ones that each element in the domain maps to each element of the range, like one element of the range mapping to only one element of the range. Domain is my x values, the range are the y values, right? Domain is x, range is y, independent variable is x, dependent variable is y. Things always depend on their independent variable. We talked about all these diagrams that we can use. We talked about the notation, the function notation, f of 1 being if the x value is 1, what's the y value, all that good stuff. We sketched some graphs, talked about domain and range. Then we did this, the difference quotient thing, right? We talked about how we can have the difference in the x values and then showing a difference in our y values and finding the general change in y divided by the change in x. And that was kind of like a general slope type deal, which we'll get into a lot later on. Kind of jumping back to ways to represent functions. There are really 4 possible ways to represent functions. And we can talk about them verbally, numerically, visually, algebraically. In other words, description in words, description in tables, by a graph, or by an explicit formula. And the nice thing is that we can use those to kind of complement each other. We can use those to complement each other in that we can say, okay, if we look at the graph, how does that relate to how we look at the table? If we look at a table, how does that relate to how we look at the formula? If we look at the formula, how do we look at it in the graph? If we look at the formula, how do we define what that means in words, right? And we can use those to go hand in hand to form a full picture of what's going on. And we'll do that a lot in here. I'm going to be asking you to really be able to visualize what's happening on the graph so that you can kind of understand what's really going on within a function, what's really going on within a certain situation. For example, the area A of a circle, we talked about all of these yesterday, but let's kind of like re-examine a little bit. The area of a circle depends on the radius of the circle. We talked about that. We have our formula, pi r squared, right? But the best way to talk about this would be looking at it as its function. But what if we looked at it in terms of its graph? Really, in essence, what is this pi r squared? 3.14 times r squared. Isn't squaring something a quadratic? So really, this function is a quadratic function. We don't really think about it like that, but pi r squared is truly a quadratic function. It bounces off the origin, going up to the left and to the right, and it's a 3.14 vertical stretch, right? Does that help us in any way to try to understand the topic? Not really. It doesn't really help us, but it's just another way to think about it, another way to look at it. Human population of the world depends on time. Population versus time. They had presented it to us as a table, but really, could we create a scatter plot? Could we visualize it? Yeah, that might be really good to see. Trends in population. Mailing an envelope. They didn't even give us the function of this, but maybe we could create some sort of scatter plot. Maybe we could see what it's like as a table to try to wrap our minds around it. This is a great representation of a visual graph. Would it make sense to look at it in terms of an equation? Probably not. And it might not really help us in that respect. But it's a great way to see it as a table. Great way to see it as a graph. Maybe looking at a table might show us something different about it. So there's different things that we can do based on how the material is presented to us, how we can change it so that we can see it in a different light. Okay. All right. So, for example, I know this is like I do this example with my Algebra 1 students. It's funny that it's also in this calculus book, though. When you turn on a hot water faucet, the temperature T of the water depends on how long the water has been running. Draw a rough graph of T as a function of time that has elapsed since the faucet was turned on. Go ahead and make a rough sketch for yourself. Draw a rough sketch, a rough graph of T. What is T? T is temperature of the water. You turn on the faucet, you crank the hot water on. What happens to the temperature of the water since the time as time goes on? Label your axes. Draw a rough graph of temperature as a function of time since the water was turned on. All right, I'm going to think about it like this. First off, how do I know what goes on what axis? Well, temperature as a function of time. Okay, that tells me right there what my dependent and independent variables are. Temperature as a function of time. That means my independent variable is time. As time elapses, as time is on my x-axis, temperature will be on my y-axis. As time elapses, what's going to be my temperature? Well, let's say, it's not really going to start at 0 as the temperature. So let's maybe, I don't know, maybe this is 0, 20, 40, well, no, it wouldn't start that low at all. Let's go 0, 50, 100, 150. Let's go by 50s. I don't know. We're just kind of ballparking here, right? And let's say minutes. 1 minute, 2 minutes. 1 minute and 2 minutes. And okay, it's probably going to start out somewhere roughly around like 75 degrees. I don't know. It's probably somewhere in there. And you turn on the hot water. Does it automatically start getting hot? Not my water, especially if I'm up in my bathroom. It's like cold, 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 cold. For like the first 30 seconds, it probably stays where it is. And then the hot water starts to get from the tank to the faucet. And then it starts to increase, right? And then at some point, does the water keep getting hot and hot and hot and hot forever and ever? No, your hot water heater is set to a certain temperature, and it will get that hot. Maybe like it's like 110 degrees. I don't know. What's the boiling point of water? 212. Thank you. I knew somebody would know that. You guys are smart kids. It goes up and up and up, and then it kind of levels off, right? And I guess if I would continue this on and on and on, I don't know, for like a half hour, what should eventually happen to the water? It should go back down again, right? You run out your hot water tank, and then it's probably going to go back down again. And then your mom yells at you because you use up all hot water. Why do we do this? Why are we doing this? This is really just taking a verbal description, a word description of what's happening, and turning it into a graph to try to understand it a little bit in a different way, to think about it in a different light. That's a lot of what calculus is. It's a lot of thinking about, given an equation, what does the graph look like? Given an equation, what does the derivative look like? What does that imply about the graph? Given an equation, what does the integral look like? And what does that imply about that graph? And we'll go back and forth with those things. So we'll be using a lot of we'll be shifting a lot of different ways to look at the graph, ways to look at the function. Okay. All right. A rectangular storage container with an open top has a volume of 10 meters cubed. The length of its base is twice the width. Material for the base costs $10 per square meter. Material for the sides costs $6 per square meter. Express the cost of materials as a function of the width of the base. So what we're doing in this example is creating a function. Creating a function based on the words. What should my function be in the end? Well, look at the last sentence. The last sentence is usually, of any of these word problems, usually going to tell you what the function should look like. Express the cost of materials as a function of the width. Express cost as a function of width. So in the end, I am going to have a cost as a function of width. Cost as a function of width. That means in my equation, I should only have width as my variable. And the end result should give me an equation that's going to generate cost. When I plug in the width, it's going to give me cost. All right, so I know my regular storage container has to have a volume of 10. Has to. So I know volume is equal to length times width times height. Let's draw this. It's always a good idea to try to, visually see what's going on and see if that can assist you in solving the problem. So I've got volume is equal to length times width times height. I'm told that, okay, let's make this length, width, and height. I'm told that the length of the base is twice the width. So what can I put in place of L? 2W, right? I can say this is not L anymore, this is 2W. So right now, we've already eliminated one variable, right? I only have H and W now. And in the end, I only want W. Okay, so we can say this. The volume is equal to length, which is 2W, times W, my width, times my height. But I know what volume is. Volume is 10. Volume has to be 10. So I'm going to make that 2W squared times H now. Now, I don't know how that's going to help us, but I know that we have an equation there that I could pretty easily solve for H, or I could pretty easily solve for W, right? If I just scoot all that other stuff over to the other side, boom, I've got an equation where I can solve for W or solve for H pretty easily. I know in the end I only want W, so this might assist me here. The other information that I have is all about my pricing. Material for the base costs $10 per square meter. Material for the sides costs $6 per square meter. So let's talk about the material for the base, the cost of the base. I know that the cost for the base, is going to be equal to $10 per square meter. Okay, so it's $10 times the area. Well, what is the area of the base? What is the area of the base? 2W squared, right? Looking at the base there, I've got my dimensions as W times 2W, so 2W squared. And notice here that it says at the very beginning, a rectangular storage container with an open top. That's why I'm not doubling it, because I only want the bottom. I don't need the top. So it's just W times 2W, so 2W squared. So all in total, 20W squared. Just for the base. That's the cost of the material of the base. Okay, so material for the sides. Cost for the sides is going to be equal to, well, it's $6 per square meter. So what is the what is the total area of the sides? Well, the sides vary a little bit, right? The sides are going to vary a little bit. We should write this as an open top too. So there you go. Maybe visually there. Okay. The sides are going to cost $6 times the area. So what is the area here? Well, think about the front and back face. The front and back face are both WH, right? That's the area. So I've got two of those. Two WHs. The material for the sides, the left side and the right side, so this side over here, this is, well, H times 2W, so 2WH in and of itself, right? But we've got two of those. So 4 WH. Right, 2 times 2WH. Right? This front side is WH. This side is 2WH. 2W times H. So I need two of these. That's where I got my first 2WH. And then I need two of the sides. I need left side, right side. So 2 times 2WH. So all in total, 6 times 6 WH, or in other words, 36 WH. Okay, follow me so far? Okay, now I can write out the whole cost, right? I can write out the entire cost. The whole cost is going to be equal to 20W squared plus 36 WH. So I'm almost there. I almost have a cost function with only W as my variable. However, there's that one little tricky H that's sitting on the end of my cost function. How do I get rid of that H? How do I get rid of that H? Well, I revert back to another piece of information that I've already gotten. You see what I can do here? If I divide by 2W squared, that's going to be 5 over W squared is equal to H. I have a little equation that I've solved for H. I can now input 5 over W squared in for H. Cost, as only a function of width, is 20W squared plus 36 W times, instead of H, 5 over W squared. So simplify that just a little bit more. Cost as a function of width is 20W squared plus 36 times 5 is 180, I think. Yep, 180. And we cancel one of the W's, 180 over W. There we go. And there we have it. That's fully simplified. I guess if I wanted to pull out a W and a 20, I could do that, but that doesn't really change anything, right? I love when freshmen are dancing through their classrooms. All right, question about that one. Question about that one. Okay, now why did we do that? Well, this is all about creating the function based off of words. We're going to have to do this from time to time. We're going to have to do this where we take words, we take a description and create a function out of it and try to wrap our minds around it so we can get to what we need, right? We wanted only a cost as a function of width, so we needed to figure our way around getting our H out of there, simplifying the expression all down, working it out, doing the algebra. All right, let's jump back to domain here for a minute. Because there's going to be often times where I say, is the domain restricted at all? Is the domain restricted at all? So what types of functions restrict the domain? Well, here are two types of functions that restrict domain. What would the restriction on the domain be for A here? Or what values can't I plug in? What value can I not plug in for A? F of x is equal to the square root of x plus 2. Would I be able to compute x equals negative 5? No. Would I be able to compute x equals negative 10? No, because I'd take negative 10 plus 2 is negative 8, and then square root of negative 8 would be non-real, right? So I have to restrict my domain. How do I restrict my domain? Any number bigger than, well, be careful. Can it be 0? Yes. Can it be negative 1? Can x be negative 1? Negative 1 plus 2 is positive 1. So x can still be negative 1. Any number bigger than negative 2. You set the inside greater than or equal to 0. The inside of the square root has to be positive. The inside of the square root has to be greater than or equal to 0. We subtract the 2 over to the other side. X must be bigger than negative 2. Can it still be negative 2? Yeah, I can take the square root of 0. That's totally fine. Whenever you're looking for what values cannot be plugged in for a square root, you set the inside of it greater than or equal to 0. Now, how do we write that in terms of interval notation? Well, we say bracket negative 2 to infinity. Inclusive on negative 2, going up and beyond greater than or equal to negative 2, so up to infinity. All right, now, how do I have to restrict the domain for a rational function like part B? Remember, rational functions are ones that can be expressed with fractions. fraction functions, you cannot have zeros in the denominator, right? Okay, so if 0 can't be the denominator, well, you just say this. The denominator cannot be 0. And then you solve that equation. The denominator cannot be 0. Well, x squared minus x cannot be 0. Let's factor out an x. Oh, cannot be 0. And we solve that equation here. So, okay, the zero product property. X cannot be 0. X minus 1 cannot be 0. So x cannot be 0. X cannot be 1 if I add the 1 over to the other side. Now, the tricky piece to this is writing it into interval notation. Whenever you have a not equal to, it's really tricky to write as interval notation. You got to use union symbols. Okay? You got to use union symbols. So we say, okay, anything below 0 can be a solution. So from negative infinity to 0 can be a solution, right? As well as anything between 0 and 1. As well as anything above 1. Oh, to infinity. Oops. Or to 0. That's what that would look like. That's
Sorry.
I saw it happen.
Yeah.
Now, this is interval notation. Honestly, this is an instance where it might be, throwbacks, interval notation, or to set builder notation. That's what it would look like in set builder. Now, that's one case where it would actually be easier to write it as set builder notation. But more often than not, where you're going to be using interval notation, I don't care either way. Just make sure you write it in a correct type of notation. Set of all numbers x such that x is not 0 or x is not negative, x is not 1, or this. Negative infinity to 0, not including 0, right? Can't be 0. From 0 to 1, not including 1, and beyond. All parentheses there. Okay, we've learned this many times before, the vertical line test. Remember that the vertical line test tests visually if something is a function. We're talking all about functions here, right? This is a visual representation of is something a function or not. Draw a vertical line on it. If it can hit twice, then it's not a function. A curve in the xy plane is the graph of a function of x if and only if no vertical line intersects the curve more than once. So, for example, obviously here, the vertical line test does not pass the vertical line test on the right side. There are two x values that have, there's one x value that has two different y values. That cannot happen in a function. Okay? If it ever overlaps like that, it does not pass the vertical line test. Talk about piecewise functions. Now, I cannot remember. I think you guys learned piecewise functions last year in pre-comp, right? I think so. Back in Algebra 2, I think this is the thing that got left behind in quarantine. Like, we decided not to do anything out of Chapter 9, so we never covered piecewise functions. I don't think. So this is something that if you had us there, I don't think we did this. The functions in the following four examples are defined by different formulas in different parts of their domains. These functions are called piecewise functions. When functions are defined by their domain, and you have different pieces of the domain referring to different types of functions, that's called a piecewise function. So say, for example, we've got this function, f of x is equal to 1 minus x as long as x is less than or equal to negative 1, but x squared if x is greater than negative 1. So do you see how there's a boundary here? At negative 1, to the left of negative 1, it's defined by something, but to the right of negative 1, it's defined by something completely different. To the left of negative 1, less than or equal to negative 1, it's defined by the linear function 1 minus x. 1 minus x. To the right of negative 1, it's defined by the quadratic function, the quadratic parent, x squared. Okay? So let's evaluate negative 2, negative 1, and 0, and then use it to sketch the graph. All right, so for any piecewise function, you take a look at the input, see where the input tells you to go, and then follow that rule. So negative 2, because negative 2 is less than or equal to negative 1, I use the top rule. right? It falls into this domain, so therefore I'm going to use the 1 minus x rule. Okay, so 1 minus a negative 2, so that's 3. F of negative 2 is 3. Now, the tricky part is when it falls in the boundary. You have to figure out where does it fall and which piece has the or equal to. I guess it's not really tricky, you just got to use the rule. So for example, it's negative 1 here. It tells us to solve for negative 1. It tells us to solve for f of negative 1. Well, f of negative 1 is the boundary. So what rule do we use? Well, look for the or equal to. The or equal to is going to tell you what rule to use. So use the top rule again. 1 minus a negative 1, that's going to get us 2. F of negative 1 is 2. And then we have f of 0. Well, f of 0, because 0 is greater than negative 1, we end up using the bottom rule. Well, 0 squared. So f of 0 is 0. So this gives us 3 coordinates. 3 coordinates that we can use. So let's sketch it. Okay, so we've got, put it in red here. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2. Okay, so my first coordinate here is at negative 2, comma 3. Negative 2, comma 3. My second coordinate is at negative 1, comma 2. My third coordinate is at 0, 0. Based on these 3 points, it may be tempting to just like draw your line in between them and be done with it, right? That's tempting. However, our knowledge about piecewise functions says that on the left side of negative 1, it's linear, but on the right side of negative 1, it's quadratic. So we have to be very careful about how we graph this thing. I like to do this. I like to put a dotted line at the boundary. That's just like a Mr. Laverick thing to do. That's not like an actual piecewise function thing to do. That's just something that I like to do to remind myself that on the left side, it's going to look completely different on the right side. All right, on the left side, it's linear. So I've got 2 points on the left side that I can just continue my straight line. I only need 2 points to define a line. So I've got them. I'm done. I can just extend my line through those 2 points. Now, on the right side, it's going to look quadratic. So say 1, comma 1, 2, comma 4, 3, comma 9. It's going to look like this. Now, what's going to happen leading up to the boundary line? Well, at negative 1, if I were to plug in negative 1 into x squared, I would get positive 1. It would be negative 1, comma, positive 1. So what I do here is I say, okay, leading up to the boundary line, I go to graph that point, and instead of actually doing the point, I do an open circle. Why an open circle? Well, because it was a not or equal to here. It's never going to reach negative 1, comma, positive 1. If I look at negative 1, it's going to be negative 1, comma 2, not negative 1, comma, positive 1. For every point leading up to the boundary line from the right side, it's going to look like that quadratic. So like if I were to graph 0.5, negative 0.5, that would give me negative 0.5 squared is 0.25, right? So that would be here. And I could keep plotting those points, but looks like I made it. There we go. I could keep plotting those points up until the boundary line, and I'm going to get closer and closer and closer to that boundary line. But do I ever reach the boundary line along that quadratic? No, because I'm never getting, or I don't have an equal to negative 1 on that quadratic. The equal to negative 1 is reserved for the linear one. This closed circle is right there, jumps. We'll call that a discontinuity later on. Fancy word for it. Okay. All right. Last couple things here. Sketch the graph of the absolute value function f of x is equal to the absolute value of x. What I'm going to look at this, the way I'm going to look at this is actually through the piecewise function lens. I'm going to define the square root, not square root, the absolute value of x to be a piecewise function. What do I mean by that? Well, if I've got f of x is equal to the absolute value of x, there are kind of 2 rules to follow for absolute value, right? if the absolute value of a number, like, and we're looking at a number, and that number is positive, if I take the absolute value of a positive number, what happens? Nothing, right? It stays the same. The absolute value of positive 4 is positive 4. The absolute value of positive 10 is positive 10, right? If I plug in 5, I get 5 out. If I plug in 10, I get 10 out. So f of x is equal to x for all positive numbers if x is greater than or equal to 0, right? If x is positive, it's just the same number, right? If x is positive, it's just the same number. So what would happen if x was, greater than symbol. If x was negative, if x was less than 0, what should be my rule to follow? So I plug in -2, the absolute value tells me to chop off the negative sign, turn it to +2. So what should be my rule? What would I write over there? What do you think? What do you got ideas? -2 is going to turn into +2. -3 is going to turn into +3. -10 is going to turn into +10.
So just negative x?
Negative x, exactly. And that is the rule for an absolute value. That's the piecewise way to represent the absolute value function. And we're going to look at the absolute value function is kind of like a unique type of function that, in terms of, looking at it in like as compared to a quadratic will curve at the bottom of it. Doesn't the absolute value function come to a nice clean point, right? It doesn't curve. It actually comes to a what we're going to call a kink in the graph. I know it's weird, but it comes to a nice clean point in the graph, and that's very unique, and that's something that only happens very, not very often. Okay, so we're going to be talking about the absolute value function as some sort of unique, weird thing that we have to kind of almost have separate rules on sometimes. Okay. And then the last topic we'll talk about is symmetry, even and odd functions. You talked about that last year in pre-calc. This symmetry will help us a lot when we start graphing by hand. We know that if it's got some sort of symmetry, then we can use some rules on it. Let's remind ourselves what even and odd functions are. If a function satisfies this rule, f of -x ends up being f of x, then it's even. What does that mean? That means if you can plug in -x into the function, whatever that function may be, if you can plug in -x and it doesn't change anything, that's even. If you can go to the function and you can plug in -x and it's not going to change anything, you get back out f of x like you started, then it's even. Like, for example, x squared is even. F of x is equal to x squared is even, because if you take x squared and you plug in -x, negative goes away, because when you square any negative number, it turns back positive. And isn't that the same thing that we started with? Look, f of x is x squared, f of -x is also x squared. That's an even function. That's what we mean by even functions. Even functions are symmetrical about the y-axis. So visually, this is one of those things where we talk about it in terms of algebraic properties versus visual properties. What does that look like? Well, algebraically, it looks like f of x is equal to f of -x. Visually, it looks like it's symmetrical about the y-axis. Okay. Odd functions. If it satisfies this rule, f of -x is equal to -f of x. If we plug in a negative and we can remove that negative and put it out in front, then it's odd. F of -x end up being -f of x, then it's odd. Visually, like x to the third is odd, because it almost rotates around the origin, right? You can reflect over x and y, and then you can see the x to the third. Like, if I plug in a -x, well, -x to the third power, that negative stays, right? So this is technically negative x to the third. That negative can come out in front of the function and sit out in front. And isn't that negative f of x? So we just said that f of negative x equals negative f of x. If we can use that rule, then it is odd. Okay, then it's odd. So let's practice that a little bit. Determine whether the functions are odd, even, or neither. Well, the test is to plug in negative x and see what happens. So let's see what happens with f of negative x. Let's see what happens for this first one. Might have to erase a little bit. Okay, well then it's negative x to the fifth plus negative x, right? Well, for any odd-powered variable, the negative is going to stay. The negative can get removed, just like x to the third. The negative can come out in front. So this is f of negative x, negative x, is equal to negative x to the fifth, right, minus x. Okay, well, do you see how I have two negatives inside there? Can I remove the negative? That's the test to really see if it's odd. Can I remove the negative and factor out a negative and pull it all the way out front? Let's try it. Negative x to the fifth plus x. Look at what we started with. Look at what we finished with. So this is truly f of negative x is really equal to negative, and then look at that. Isn't that f of x? That's the rule for an odd function. So we can say definitively this is odd. If you can plug in negative x and factor it all the way out to the beginning, I'll factor that negative all the way out to the beginning, then it's odd. And when I say factor it out, I mean factor out that negative and it comes back to the same thing you started with once you factor it out. That's odd. Take a look at B. Let's see. Let's plug in g of negative x. Well, this would be 1 minus negative x to the fourth power. For any odd-powered function, for any even-powered function, what happens to the negative? Goes away, right? Negative x to the fourth turns into just positive x to the fourth. So g of negative x is really equal to 1 minus, well, that just goes to x to the fourth, right? And isn't that what we started with? Can't we make the statement now, g of negative x is really equal to g of x, 1 minus x to the fourth. So that is the rule for an even function. If we can plug in negative x and it doesn't change anything, we get back what we started, we know that it's even. And let's take a look at our last one, h of x. Let's plug in h of negative x. So this is 2 times negative x minus negative x squared. All right, 2 times negative x, that's negative 2x. We can pull that negative out in front and make it negative 2x. And then this is minus, and then this negative x squared will turn positive, positive x squared, but we know it's a minus sign in between it. Okay, it didn't leave it the same, right? So maybe I can factor out the negative. It's not even, so maybe I can factor out the negative and turn it odd. Okay, if I factor out the negative, that would be negative outside, 2x plus x squared. Did I get back what I started with? No, I didn't. I wanted 2x minus x squared, and I got 2x plus x squared. So it's not even, and it's not odd. It's neither. It doesn't have a symmetry. Sometimes it doesn't even have a symmetry at all. It could be odd, even, or neither. This one was neither. The last thing that we'll cover is increasing and decreasing functions. Increasing and decreasing functions. Honestly, all increasing and decreasing functions is like, is the function going up or is the function going down? Very simple. Is the function going up or is the function going down? Like, for example, you're going to have to, in your homework, you're going to have to define, okay, give me an interval where this function is increasing. Okay, quite easily, the interval from A to B. That's increasing, right? It's going up. The function is going up. Or I could have said, likewise, from C to D. That's an interval where the function is increasing. The only interval where the function is decreasing is from B to C. That's it. Right? That's what I mean by increasing and decreasing. I know this is a very simple thing to visually see, but increasing and decreasing function, that's going to be extremely important later on when we talk about the graphs of the derivative and how they relate to the graph of the original. So you're going to have to tell very often whether the function is increasing or whether the function is decreasing to be able to learn about how the derivative is going to work as well. So the function is increasing from interval A to B or C to D. We could write it like this. Say the x values are A and B. The function is increasing along the interval A to B. And also, we're getting real fancy, and also from C to D, right? That's when it's increasing. From A to B, the x values A to B, but also the x values from C to D. It would be decreasing using interval notation from B to C, from the x value B to the x value C. Somebody brought up last year, do we have to use brackets? Is it truly inclusive? And I would say probably not, because what's happening at C? Is it continually increasing or decreasing at C? It doesn't make sense that it's like bracketed on both increasing and decreasing. Like that doesn't make sense really. What we're going to find is at C and at point B and at point C, those are unique points. They're maximums and minimums, and they no longer are increasing or decreasing. They are points where we've got a peak or a valley. So it's not really increasing or decreasing, but it does have unique properties as well. So if you use brackets, totally fine. If you use parentheses, totally fine. Doesn't really matter to me. Okay. All right. So tomorrow, I'm so sorry I did get long-winded. There's only 6 minutes left to class. Tomorrow, the entire period is yours. Trust me, I won't talk at all. I promise. You'll have the whole period to work, and I will not bother you unless you ask me questions. Then I'll bother you.